Lean 4 operates on the Curry-Howard correspondence. The Curry-Howard correspondence is a theoretical result establishing a precise structural isomorphism between computer programs and mathematical proofs. Under this framework, a formal type acts as a logical proposition. The program that successfully inhabits that specific type signature serves as the mathematical proof of that proposition. Leonardo de Mora initiated this architecture at Microsoft Research to bridge the historical gap between automated theorem proving and functional programming. To achieve this, Lean 4 relies on a complex elaborator, hygienic macros, and recursive type class inference. Type class inference is an automated resolution procedure that synthesizes necessary mathematical structures and axioms for a given type behind the scenes. While powerful, evaluating these mechanisms makes large-scale verification computationally demanding. Treating Lean 4 purely as an informal blackboard and ignoring this underlying complexity causes immediate issues. The unification engine quickly becomes overwhelmed, leading to severe compiler timeouts and proof rot. Engineering formal mathematical certainty requires adherence to architectural best practices, immutable environments, and precise API boundaries. In Lean 4, rigorous software engineering is a strict prerequisite for maintaining mathematical soundness at scale. Lean 4 theorems are highly sensitive to minor elaborator changes across compiler versions. Reproducibility requires a perfectly deterministic workspace. ELAN acts as the toolchain synchronizer. It reads the Lean toolchain file to automatically provision and pin the exact compiler release across all machines. This strict pinning ensures theorems true in one release don't break in the next due to routine changes. This code block shows the entry point of a compiled Lean executable. Project compilation, execution, and dependency resolution are handled natively by Lake, the Lean package manager. Lake generates a Lake manifest.json file. This acts as an immutable lock file for external Git hashes, preventing version drift between local environments and remote repositories. Because dependent types require intense verification overhead, compiling foundational libraries like MATLib4 directly from source consumes hours of CPU time. To minimize initialization latency, the community standard relies on the terminal command lake-exe cache get. This command bypasses local compilation entirely by pulling precompiled .olean binary artifacts directly from remote community servers. Executing this cache retrieval drops environment setup time from several hours to a matter of seconds. Without pinned toolchains and remote binary caching, the immense computational weight of formalization would collapse the ecosystem scale. At the syntactic level, Lean 4 enforces a rigid naming taxonomy derived directly from its underlying type hierarchy. These naming conventions are immediate semantic signals of a term's specific type universe. The highest tier, types and structures in type, uses upper camel case. The second tier, logical propositions in prop, uses snake case. Because all proofs of a proposition are definitionally equal, they are erased during extraction, carrying no computational payload. The third tier handles executable functions using lower camel case. This strict visual taxonomy allows developers to instantly differentiate between computational logic and mathematical verification while scanning a massive codebase. Automated linters enforce this taxonomy. Deviating from capitalization rules triggers immediate compilation failures during continuous integration. Lean also mandates standardized docstrings and strict 100-character line limits to ensure the generated HTML API references remain legible. This visual taxonomy acts as the critical connective tissue that allows hundreds of researchers to seamlessly read, review, and debug a monolithic codebase. During interactive development, the Lean language server protocol dynamically evaluates the proof state in real time as the user types. Massive monolithic tactic blocks completely overwhelm the complex unification engine, ultimately causing the compiler to hang and freeze. Tracking dozens of local hypotheses forces the language server's memory limits to redline, triggering deterministic allocation timeouts. The required practice is to aggressively modularize code into small, isolated lemmas that the build system evaluates independently. This modularity restores IDE responsiveness by strictly limiting the search space required by the elaborator and the tactic engine. Developers rely on the sorry macro to temporarily bypass hanging subproofs without stalling the compiler. The second critical performance concept relies on managing transparency levels to control exactly how definitions unfold during type checking. Lean utilizes two distinct keywords for introducing intermediate variables inside a proof: let and have. The let keyword keeps the definition transparent, allowing rewriting tactics to observe its internal construction. Conversely, have makes the definition completely opaque, establishing a strict API boundary. This prevents automated tactics from spiraling into infinite reduction loops by actively hiding unnecessary implementation details. Mastering these API boundaries is the exact difference between a proof that verifies instantly and one that hangs the compiler indefinitely. These structural best practices allow Lean 4 to function as a fully self-hosted ecosystem. Because the compiler, elaborator, and tactic engine are written in Lean itself, the architecture provides a unified and seamlessly extensible programming environment. MATLAB 4 serves as the ultimate validation of this architecture. It is a monolithic, community-driven mathematical library that scales to nearly 2 million lines of formalized code. MATLAB 4 relies entirely on automated type class inference and these exact naming conventions to ensure that mathematical theories interact smoothly and avoid knowledge siloing. Beyond pure mathematics, Lean 4 sees rapid adoption as a mission-critical verification engine for industrial engineering. AWS formally verifies Cedar, its open-source cloud authorization policy language, directly inside the Lean 4 environment. AWS engineers construct an executable semantic model of Cedar to mathematically prove security properties across all conceivable computational states. Lean extracts these verified models into highly optimized native C binaries, enabling differential testing in live production environments without any runtime overhead. As AI labs train models to auto-formalize logic, Lean acts as the absolute oracle for mathematical truth. By linking formal logic to standardized engineering practices, Lean 4 provides the infrastructure for verifiable computation.